last day we did all the forward kinematics using this Clifford algebra. You can do the same, different two forward kinematics. The absolute from the the fixed frame to the end effector, or the relative from one position of the end effector to another position of the end effector, still measured from the fixed frame. You can do it with the dual quaternions. You can do it with the matrices. It's just different algebra that you can use. But because we will use that in the design, then that's one of the key tools that we will have, is the forward kinematics. We also mentioned the inverse kinematics, and we may go more into that. But because this class is about design, and what we want to do is to design robots, let us talk a little bit about the design process. And I don't know if we did that already. Did we talk about the design process at the beginning of this course? You guys remember? No? No? Okay. So let's do that. So basically, we are going to just say a few things about the kinematic design. So our goal is to have some articulated system, a system that is made of joints and links. And what we want to do is to create these systems in order to perform a specified motion. Okay, so that's the idea of the kinematic design. This is what we call kinematic synthesis, right? Synthesis. We have the motion, and we want to create. So here is the motion, and now from the motion we want to create an articulated system. So we need to know, what kind of links, what kind of joints, how many links, what are the dimensions, how many loops we have in the system, where it is located, in order to be able to do some motion. Right? But the easy way is the other way. You already have your robot and you analyze the motion, right? So this way we have analysis. That's the easy one, right? If you know your tricks, you can do it. In this direction we have the synthesis. It's the design, the creation, you make something new. All right? So it's challenging, but it's also rewarding. So in the kinematic synthesis, there are many steps, right? As we said, you may want to know the basic topology that you can apply, right? And that's called the type or structural synthesis. Synthesis. So it's like, yeah, I want to do this motion, or I want to do this set of motions, or I want our robot to move in this space. But what kind of joints do I use? Is it a parallel robot or just a serial manipulator? How many links? So that's what we call the type of structural synthesis, that determine the structure, right? What we call, I'm not sure if it's very precisely what we call the topology. So select the topology of the system. And I think we can summarize all that on number of joints, number and type of joints, and if you know the joints, the links will come because they will join the joints, right? Number and type of joints, the connectivity between them. It's basically just the graph, right? So this joint comes after this one, and then the number of loops, which is given by this connectivity in the system. So basically defining your graph. I want to create this motion with serial manipulator with 3 revolute joints. That will be one. Remember, we did that seminar on graphs, so we are not going to cover here, but it's a useful tool. So you could think of, R, ground link, and effector. Sorry, one more R. And this should be the links. So this will be a serial 3R manipulator. Our linkages will always be grounded. No, we are not doing mobile robots or flying robots, so we'll always have a ground link. So this is a very active area of research, and basically it's, this is an enumeration problem. That's what basically is. You need to say, for this, and that's not solved yet. For this task, I will need all that. It's more, with this number of joints, with this number of links, with this number of loops, I have all these possible graphs that could be applied, because there are many different ones. And those are all, create different linkages, and that's the next problem. What we don't have yet is, for this type of tasks, this kind of topology is more suited to it. That doesn't exist yet, so that's completely open field of research. Okay, there is a lot of enumeration, so people will say, these are all the possible graphs of linkages with 10 links and 3 loops, and you have this big table, so that there is a lot of papers on that. So it's an enumeration problem and then a searching on all that big database of linkages problem. That's basically what it's being done. So not solved yet. Unfortunately, we don't have this. We can create our task and then press a button and see all the possible. That would be really nice. Someday we will have it, but doesn't exist yet. We don't do this. Okay, we are not. This is not our specialty. But somehow you have to deal with this. You cannot avoid it. But then once you have selected the topology, more or less, it seems that it will going to work. Then you have to do the next step, which is the dimensional synthesis. Now you have to actually give dimensions, locate your joints, basically. And that means, now you know that this robot has 3 joints. See how far apart these joints need to be, at what angles, in order for them to reach the positions we want. And that can be, summarized in selecting the location of the joints, the position of the joints, basically. Select, or in our case, it's not selecting, it's calculate. We do have equations for this. Calculate the position of the joint axis. Axis in order to, I would say, reach the task, or to be able to perform the task, or to go as close as possible to perform. If we do exact synthesis, we do, we have to actually do that task that we define, or go as close as possible. This would be approximate synthesis. Go to the task. Once you know the position of the joint axis, then you know the distance between them, so you know your link. And lately we have been working on the realization, which is quite obvious, but until you start designing, you don't notice that many different links will work, but they will give you the same task. So you can put a link here, or you can put a link here. They will do the same task. They will have different properties, like dynamic properties and force transmission and things like that, but the kinematic task, the motion, will be the same. You can put this link anywhere along your joints. So basically, just defining the joints, you define the kinematics. The rest is, other specifications. So this is what we are going to cover mainly in this course: how to create these equations so that we can design to perform, a given task. And what is the task? Right now it's kind of undefined. So let's talk about the task. The task. A motion. We are talking about kinematic tasks, so that means a motion. A motion and its derivatives. So position, velocity, acceleration, blah, 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 blah. Okay, I want my robot to pick up something here, take it there, stop there smoothly, things like that. And this can be done or can be made as complicated as you want. We don't want to do it very complicated to start with, but the simplest way would be define a positions, pick and place kind of thing. I want my n effector to be here at certain moment, and then I want it to drop something here. That's the simplest. So the task can be defined. As, first of all, a set of positions. That's those are transformations from the fixed frame to a moving frame, basically. A finite set of positions, and this is called finite position synthesis. Right? A finite set of positions, which will be something like this. Here is our fixed frame. I'm going to define a moving frame that it has to go from here, passing through here, up to there. So position 1, position 2, position 3. And I want some kind of articulated system able to do this. Whatever it does in the middle, I don't care, when we define this. This is the simplest case, and that because it's the simplest, this is the one we are going to deal with first and most, basically. There is even a simple case in which you don't care about the orientation. You just define a set of points. A finite set of points. So it's like, okay, I want the robot to touch these points at whatever orientation it touches it. I don't care. That's even simpler, right? So I want it to pass through here, through there, through there, and through there, and the orientation could be whatever needs to be. That will be the simplest. But in robotics, most of the times we care about the orientation. You think about placing things or inserting, even pointing. Almost any task requires orientation. Finite set of positions, a finite set of points. That will be the easiest case. Then we can go a little bit more sophisticated and now ask for a trajectory. It's a curve in space. That will be the next. A trajectory or path. Usually we distinguish between path and trajectory. We call path when we don't care about the time. It's just a geometrical curve in space. Trajectory, we call it when we care about the time. So it has to pass through this point at t1, so you have a time stamp associated to your task. A trajectory of path, and that could be of, a rigid body, location plus orientation, or it could be just point. So it could be point path, or a rigid body guidance. And basically, if we were going to draw this, I'm going to draw both at the same time. So a point path would be just a curve here. This is the curve I want my robot to follow, the end effector, and you could select a point. It could be the center of the end effector frame, a tip of a tool, something like that. Rigid body guidance. You will have to define position and or location and orientation. So imagine, a little frame associated to each point. Okay, it's kind of looks like a worm or something, but many times what we do is we define a cube and move the cube or any other object. It's very easy to go from this to this. You can just think of this as a set of points as close as possible, and then use finite position synthesis or a set of positions. That's the way we usually do it, but you could also define, just algebraically this curve. I want it to trace a circle, or I want it to trace a spiral, and you could define that and try to do the synthesis for that exact curve. Okay, so that will be the next. And then if we go one more degree of complication, we can define a chunk of space. Oops. So we could define a volume. Volume if we are thinking about points 3D, or you can think of a hypervolume if you are thinking of on the 6-dimensional space of rotations and orientations, right? And what that means is that defines kind of like the traditional workspace. You want your robot to be able to reach all those points, okay, within that volume, okay. So it's equivalent to define the workspace. So for instance, you may say, okay, I want to design a robot that can reach any point within this volume, enclosed by this cylindrical area. And that will be, and then you may specify even more. And I want to reach every point with any orientation. I want it to be able to orient any, with any orientation within this volume. That means you are defining what we call the dexterous workspace. All the points in which your end effector is very dexterous. It has all possible orientations. Or you may define, I want this volume with a specified orientation, this angle, okay? Or it could be, whatever, you don't care about the orientation. Or you can define it in 60, and then I cannot do it, but you can say, maybe I want that this segment of my 6D space to be able to be reached, and that includes orientations and positions. So this will be the most you can define. And we can think of doing the same thing like discretizing to go to the point finite position synthesis, but it becomes kind of a little bit more complicated, right? You have to put a lot of points in order to define a whole volume. So it has been done that way, but it's not very efficient. And we have to think of other techniques. We are working on this. This is one of the things that Jim Esker is doing. Is what we call exact workspace synthesis. We define a linkage for a given workspace, and the way you do it is, you know what kind of motion a certain set of joints generate together. Given that, you can, if you want to do a parallel robot, you can intersect those. If not, you can shape those. For instance, if you know that a certain set of joints is going to create a cylinder, then just making those joints closer or the different angles, you get different cylinders. So you can actually shape that cylinder to this cylinder. Okay. But it's a more complicated problem. This is like the degree of complexity goes increasing from finite position synthesis to curve or trajectories, to the whole volume in space. We could also define planes in the middle. That's also an option. So these are the tasks we can define, and the way we define them. Oh, I forgot something else. So these are the position tasks. Then we can add velocities and we can add accelerations. Add velocities. This is something we are also doing with our partners are Fullerton, Cal State Fullerton, accelerations. Basically what you can do, and what we have done so far, and we haven't seen anybody doing anything more sophisticated, is with the finite position synthesis add a value for velocity for acceleration on those points. So you need to define first the point, then the acceleration in finite position. And I'm going to do the drawing, try you can see. Synthesis. So here we have, and imagine we say, okay, we want our robot to reach this particular transformation, and then we can add a velocity with this particular velocity direction. Okay, this will be the direction of the velocity at that point. We cannot specify the magnitude, or we can, but that's very easy. You just increase the velocity of your joints and you get a higher magnitude. So really what really matters is the direction of the velocity vector v. Okay, and then we go to another position, and then we want to define that here it has to have this, it's going to move in this direction with this particular velocity. So this is position 1, velocity 1, position 2, velocity 2, and we can do the same thing with acceleration. We can impose almost everything, but we cannot impose velocity 0. I mean, you can always accomplish that. Just make your joint velocities equal to 0, you get velocity 0. So it doesn't give you extra data for your design. Okay. But you can say how you are going to approach, in which direction at a certain point. Okay, so this is the task. Maybe we should define some, just for you guys to see it and plot it. Alright, so what we are going to be doing, it's finite position synthesis. We will do finite position synthesis, and I should say dimensional synthesis. Oh, what are you doing? There you go. Dimensional synthesis. The name becomes longer and longer. The more you define it, the longer it becomes. Finite position dimensional synthesis of robots. We will start just with positions, no velocities and accelerations. We may add those later if we have time. So let us maybe open Mathematica, and I'll show you how you can define, just as positions there. And the definition of positions is a big problem, okay? To test our algorithms, we just define random positions. But when you are going to specify a task in space, it's kind of hard to know the orientation. That's why we use the motion capture that we saw yesterday. Because then you have the position. It's given by the motion capture. So we know that to perform this action, this will be the orientation of your finger. If you need to define it just by looking, it's really hard in 3D. So that's why we use motion capture. But for our testing our algorithms, we can just Okay, so this one is working. Let me check this one over here. Yes, this one is working. Okay. All right. So, as I was saying, we were able to define positions in dual quaternion form, transform them to homogeneous matrices, and then we can easily plot them with respect to our fixed frame. And then you can see if you like the task that you are going to be using or not. Okay. So this is what we do with Mathematica: define random positions, and you can use dual quaternion or homogeneous matrix, whatever you like better. Those are absolute positions, so that means what we are defining really is a transformation. It's a displacement from the origin, from our fixed frame to a moving frame. Okay, it's a displacement, and from that displacement you can just look at any point that displays together with this frame, right? And we did it in absolute, but then you can do the relative. Maybe we should add that little part. Absolute, and then you can do relative with respect to one of them, still looking at it from the fixed frame, so we won't change that. And then we were able to plot to see if we like the task. Plot positions. So let me just do the relative, and then we'll talk about the equations next day. Okay, so let's go back to the Mathematica. These are the absolute displacements from this origin to. So the one way of looking at it is, imagine this frame was sitting right on top of the fixed frame at the beginning, and now it's here. What is the motion that has happened, right? That's the equivalent. So now we can, let me see what we put here, a set of finite positions, and then we will put absolute. And now we are going to do number 2, which is a set of relative positions. And because we are advanced Mathematica users already, we can just take this same set of positions we have defined here. Okay, here, poses, and we can just apply our equations to create the relative ones. For instance, set of relative displacements from the first position. We can take any one as your reference configuration. In this case, we take the first. You could take the 5th. Okay, position of previous example. Okay, and that was poses, right? Poses. And now what we are going to do is we are going to define poses rel, and that is going to be a table in which we are going to take poses of I, and we are going to multiply it, quad mult, by the inverse of the first position. Remember that the relative was, P12 is P2 times P1 inverse. And remember that for dual quaternions, the inverse is the same as the conjugate. So quad conj poses 1. Okay, so just this operation, that's the relative, and now I from 2 to 10. So we don't do, the first one will be identity. It will be poses 1 times the inverse will be the identity. We assume that we can reach the identity by not moving, and here you have your relative positions. And now we can plot them. Let's take just the same plot, copy and paste, and that will give us our it was this one, right? Now this is kind of harder to interpret. Now we are looking at the motion from one position to the next, so it's not as straightforward. Okay, poses rel. Oh, we need to do the matrix, right, and everything else. All right, So we need to create these matrices. Let me just put the matrices here, and we will comment them so that we don't see them because we don't care. Pose as rel from 1 until 9 because we have one less now, and then we have to create the access, which was this table over here. Oh, I should have put this matrices rel. That's fine. And now access the relative. Oh, now I have to change. Okay, maybe I won't put matrices rel. I'll just leave it in matrices so that I don't have to change the next one. Okay. Oh, up to 9. We have one less. And let me just comment it because I don't want to see it. And now access the relative. All right. So here they are. This is not very clear to understand. So this is not the motion from this frame to this frame. This is the motion from maybe position 1 that was here to position 2 that was here. Okay, so using the frame in the relative positions doesn't give you a visual understanding of what is going on, unless it happens that your first position is the origin. Then it does, but that's what you get. At least you can see how scattered they are. 1, 2, 3, 4, 5, 6, 7. 2 of them went out of our minus 10, plus 10, probably. All right. So this is all. And I think we can leave it here today, and then next day we will talk about what kind of equations we can use to dimension a system to move through these crazy positions.